video here again to show you how very small atoms are. And most of atoms are empty space and most of atoms are empty spaces because these electrons, as I've drawn them here, I have 6 protons in the center of this particular atom and 6 electrons around the outside. And the fact that I have 6 protons, I hope y'all could, we talked about this, you know it's carbon. It's a carbon atom. Okay. So we can pick on carbon. We could actually kind of go up and down. Carbon, silicon, germanium, tin, and lead actually have something in common. This is what we call the group. This is what we call the period. You might already have that on your periodic table. So elements that have lined up in a group kind of have something similar going on, and that's where we're going to pick up today. What makes them similar actually has to do with how the electrons are arranged. Okay? So the electrons, especially the outer edge electrons in the same group, are what we call valence electrons. Okay, so the term valence electrons, outermost electrons. Okay. So here we are. The valence electrons, let me grab my... One of the things I'm going to kind of try to convince you of is the periodic table I gave you. Can you see where it's matching up? I'm going to put a little split here, right here, because if you look at the periodic table I gave you, you have for your test, here's 1A, 2A, and then here's 3A with boron, 5A, 4A with carbon, and it kind of does that sort of thing. So we'll talk more about these guys. These are kind of outliers. They're a little bit, they're called transition metals. But can you see where, for instance, if we pick on fluorine and what's underneath fluorine, chlorine, you can see I'm going to circle the 7 here. 7 and the 7. Actually, in the next slide, I don't know, it's blown up for you guys, but I think this is it. So the valence electrons, I don't know if you're with me on this, but check this out. 7 valence electrons, group 7A. Let's pick on nitrogen and phosphorus. 5 valence electrons, 5A. Beryllium, magnesium, 2 valence electrons, 2A. See the pattern there? So if I ever ask you, and I'm going to ask you, we're going to go around the room, we're going to answer some questions here in a minute. Or ask you how many valence electrons oxygen has, you'd be like, oh, it's 6A. It must have 6 valence electrons along with sulfur and all that in the same group. So that's kind of fun. I like things that are like, that works. Yeah. So note that the valence electrons, the number of valence electrons, the special electrons, here in a minute, or not in a minute, in chemistry, I want to kind of dabble with putting atoms together to make a molecule. Favorite molecule we all like to kind of think of is a water molecule, and a water molecule is like this. It's got it's H2O, you guys would tell me. So we have to stick 2 hydrogens to an oxygen. And we're going to find out why does it stick together, and it has to do with the electrons. Which electrons? The valence electrons. Why do these stick together? So it's kind of fun. And then this is just a close-up. I don't know if you guys have this slide. It's just a close-up of what we just looked at. Okay. So, you know, on the sheets, and again, I tell my husband also teaches this class, or not this class, he teaches intro to gym. This is not intro to gym, but he also is a teacher, and I'm like, so I'm giving them the periodic table and saying, well, you should wait, you should put on your review sheet. So another thing you might want to put is valence electrons is equal to group number, you know, valence electrons. And that only works for the A elements. Okay, this is where we're going to go around the room. This doesn't have to do with this slide is not about valence electrons. It's about something we talked about on Monday. All right, so David, get your periodic tables handy. So David, find sodium, and you got 50-50 chance. And I'll remind you, to answer this question, we're going to find the JAG. We're going to find the JAG, okay? And this separates metals from nonmetals. So with that in mind, is sodium a metal or a nonmetal?
think I have it as in metal.
That is correct. Ding, ding, ding. Yep, and actually, this JAG does not split the periodic table evenly. So most elements are metals, okay? So we'll go back to you, Melissa, and then we'll come over here and pick you up, Genesis. So what about carbon?
I don't even see it on here.
Kind of look over here.
Abbreviation or what?
It's C. Yeah, C is the abbreviation.
So non-metal.
It is a non-metal. Yep. Very good. You got it. Kaylee. Okay, so this is one. What is the group number for chlorine? 7. Very good. In fact, I would say 7A. Perfect. This is group number 7A. Perfect. So Genesis, what is the period for the element potassium? 4. She's saying 4. I'm liking it. So remember, this is the period. Okay. Okay. All right. So back up to you, David. Give an example of your favorite noble gas.
Helium?
Yep. He's liking helium. Any of these would work. Any of these are noble gases, rare gases, inert gases. They have 3 names. Go figure. So back to you, Melissa. Give an example of an element that's halogen.
The I wonder what that is.
Iodine, yep. Now there's a few of these, and iodine might be one of them, where you're going to want to know that the name is iodine and the symbol is I. And the other, when we started the subject on Monday, I said that actually by atomic number, I gave you a list that you need to finish. Good job. All right, Kaylee, which element is, now this narrows it down to 1. That's kind of like a matrix here. So we're looking for 2A, period 5.
That's fine.
Period 5, 2A, yep, strontium. Strontium, very good. And then back up to you, Genesis. How about the element that is found in group 6, period 3?
Sulfur.
She's saying sulfur, so she put period 3, group 6A, sulfur. Yep, that's for sulfur. Very good. Okay, yet more questions. Okay, now this is the topic that we covered just this morning. So what do you think, David? Boron, how many valence electrons does it have?
Doesn't 3A.
It is 3A, so he's saying 3, and I agree totally. 3. Yep, boron, 3A, 3 valence electrons. Perfect. Okay, back to you, Melissa. So how many valence electrons does barium have?
56.
Valence electrons. So it has 56 electrons, but they aren't all valence electrons. So we're going to look at the group it's in.
Yeah.
And what's its group number? 2. Yep, so it has 2 valence electrons. Yep. All right, Kaylee, how about carbon?
4.
She's liking 4 because it's in group 4A. Yep, me too. 4. Perfect. One more. Genesis. How about xenon? It has 8. It's in period 8A, and it has 8 valence electrons. Actually, here, maybe even the next slide, we're going to see that how do I say this? Atoms like to be, all these atoms like to be electronically like these, these rare gases. Okay, so we're actually, for instance, we're going to see chlorine has 17 electrons, and it wants to be like argon, so it's going to pick up 1 electron. Now it's going to have the heart of a chlorine atom, but it's going to pick up 1 electron and be electronically, electron-wise, like argon. Okay, so these are just kind of some statistics. If I were to walk around this room, and we are carbon-based animals. We are carbon-based animals, life-based carbon and life. But honestly, when we kind of look outside ourselves, and I think we might have covered this in astronomy, most of the universe is just hydrogen when it comes to where there is an atom here or there, followed by helium, and all others in the universe is like 0.1%. 100%. I just think that is so cool. If we were to take Earth's crust, most of it's oxygen, followed by silicon, then aluminum, iron, okay? This one kind of grosses me out. If you were to take a human body, of course, we humans have a lot of water in us, so that accounts for a bunch of oxygen and a bunch of hydrogen. Not all the oxygen in our bodies is tied up as H2O. But aside from that, you can see then we have carbon. But this just grosses me out thinking you take a human body and make little piles of atoms or the different elements. Okay, so we bumped up against a assignment here. So this will be due when we meet again on Friday. Yes, there is lecture on Friday. No, it's the Friday before spring break. Could be worse. We have to have a test on Friday. Which week? They're like putting in new lights, but I feel like they're putting in fewer lights, but they're brighter. I don't know. They didn't ask me. They're cheaper too. They're the LEDs. Very good. All right. So this is like a recall or review slide. And remember, I'm kind of wanting you to know the general structure of an atom and a little bit about each of the three pieces that make up an atom. So electrons are outside the nucleus. They're kind of in this, what we call an electron cloud. They're negatively charged. They basically have no mass. Protons are found in the nucleus with neutrons. They are what identify what element an atom is. That's pretty awesome. We call that the atomic number. Atomic number is number of protons, and that's the whole number, whole red number on the periodic table. They are positively charged, and then the neutrons are kind of like Switzerland. They kind of let the positively charged protons coexist in the nucleus so close together. The weight is tied up in your protons and neutrons. They weigh about 1 atomic mass unit. So I've said that as I point to, for instance, this carbon atom I've drawn, protons for sure say what element it is. Have 6 protons, have a carbon atom. Electrons help make it neutral. We'll talk about that here in a minute. If I have 6 protons, I have to have 6 electrons if I'm going to have a neutral atom. And then neutrons actually can can come and go. Now, as neutrons kind of come and go, well, it's not that easy, but they can have we can have different variations of a carbon atom out there that have a different number of neutrons. They then make the atom weigh differently because the two things that make the atom weigh anything are the protons and the neutrons. So if the neutrons come and go, it weighs differently. So, So atoms of the same element have to have the same number of protons, but they can have different number of neutrons. Okay, so case in point, if you've heard of carbon-14 dating, carbon would be the element carbon, and in the nucleus of that particular carbon atom, it still has to have 6 protons. 1, 2, 3, 4, 5, 6. I'm going to call this carbon-14, and actually this is carbon-12. This is normal carbon. This is unnormal carbon, abnormal carbon. And the thing about it is that 12, actually, and I must have a slide coming up, that 12 is what we call the mass number. And the mass number is equal, you add 2 things together. The mass number assumes that you have looked in the nucleus of that atom and you have added the number of protons, which has to be 6 if it's carbon, and you've added the number of neutrons, which can vary. So in this case, and by the way, the symbol for the mass number is the letter A. So the mass number here, A, is equal to the number of protons. So we have 6 protons plus 6 neutrons. 12, and that's where that 12 came from. So if I go over here, I'm actually going to go ahead, I have 6 already, 6 protons, it makes it carbon. I'm going to go ahead and add 8 neutrons, 4, 5, 6, 7, 8. Okay, so now when I come up with the mass number, I'm going to put 6 protons because it's carbon, and then I'm going to actually now have 8 neutrons. Okay, so that gives me a mass number of 14. So that's carbon 14. And the way we date things with carbon 14, how does this work? Yeah. So when something is alive, and I think it has to be interacting with the sun, you and I and our dogs and the plants out there are incorporating this particular isotope of carbon into our bodies. It's there in lesser amount than that one, but it's there. After we die, and again, it's not just the sun, but after we die, this starts to go away. So this decays, and so basically then, if we wanted to dig up a dinosaur, we would look in the tissue of the dinosaur to see how much of this it had left. The lesser amount of this it has left, the older it is. So it's a very, very well-known decay rate. So that's carbon 14 dating. So mass number. See, I kind of got ahead of myself. So mass number is it's always got to be an integer because you're counting particles. You're counting protons and neutrons. Okay, so it's the number of protons plus the number of neutrons in the nucleus. So the example I have down here is uranium. I have 2 different isotopic forms of uranium. Uranium's a good one because if you're going to want to build a bomb or to kill people or a nuclear reactor of sorts to power your cities, one of these, I can't remember which one it is unstable and the other one is stable. So one will be good at nuclear fission, breaking apart, and one won't. This will be a good example. Let's pick on this, and I'll do it in the margins because we're going to have some examples of kind of detective work. So these right here, these are the mass numbers. Go ahead and take this out of the, lay it flat, it's easier to draw. Okay, so that is the mass number. Those are the number of protons plus the number of neutrons. So here's the deal. If I look on the periodic table, and again, I kind of assume I've looked at it like so many times over the last over the last many years. But uranium's down here, and it's got a red 92. So both of those isotopic forms of uranium have 92 protons. So I'm going to put 92 here. 92. And if I add them together, they equal that number. So can you see, for instance, if I take 238, I think I've got a calculator here, I'm going to cheat. If I take 238 and if I subtract from that the 92, or not. Dollar Tree calculators. So 238, I know you guys could probably do this in your head, minus 92. Okay, I'm like in 146. So 238 minus 92 is 146. So can you see where this one over here must have 146 neutrons in its center? And this guy must have what, 3 less? So this guy must have 143 neutrons in its center. See how that works? Like a little bit of detective work based upon knowing its mass number and what mass number means. And you know it has 92 protons because it's uranium. So with that in mind, let's see, we're going to kind of do these together. Okay, so we're going to kind of start over, so I'll pick on you, David, first. So we're going to do this piecewise. So David, find calcium on the periodic table and tell me how many protons it has. Calcium on the periodic table. Looks right here.
20.
It has 20 protons. Very good. 20 protons. Okay, so I'm back to you, Melissa. Protons plus neutrons, and that's what I'm trying to find out, is equal to 40, because that's what this is. That's the mass number. So how many neutrons does it have?
20.
It has 20. Very good. 40 minus 20 is equal to 20, so it has 20 neutrons. Perfect. That's it. Let's do a similar thing. So I'm going to kind of restate the problem here, Kaylee. So this version of calcium, it also has 20 protons plus the number of neutrons now is equal to 44. So how many neutrons does this one have?
24.
It has 24. You all okay with that? Okay, switching up a different element. So Genesis, you have to find krypton on the periodic table, because this isn't the number of protons. This is actually protons plus neutrons. So how many protons does krypton have?
36.
It has 36. I'm liking that. You might have to get out your calculator, David. So based upon this, 36 protons and 84 is protons plus neutrons, how many neutrons does it have?
You subtract.
Uh-huh. I would get out a calculator too.
48.
48 protons. Very good. Oh, sorry. I'm sorry. 48 neutrons. My bad. Very good. You got it. Very good. Okay. SN, Melissa, stands for 10. And I'll show you, it's kind of over here-ish. So how many protons are we talking? 50 protons. Very good. So move over to you, Kaylee. So it has 50 protons plus the number of neutrons is equal to this particular isotope of 10, which is 120. So how many neutrons does it have?
70.
She's like in 70 neutrons. Yep. See how it kind of varies? The number of neutrons is not always equal. I mean, it just kind of is out there. Good job. Okay, Genesis. W stands for tungsten. So can you find it on the periodic table?
74 protons.
Very good. She found it. It's here in the, we call these, actually, these are the transition metals. She's saying 74 protons. I'm liking it. Okay, so if it has 74 protons, you got your calculator handy, David. So how many neutrons does it have? Ten? Wait, no.
110.
Oh, sorry. Yeah. Very good. Thank you. You got it. And then last but not least, so Melissa, do you think that this will have more neutrons or less neutrons than this one?
Less.
Less. Cool. And how many less?
I don't know.
You're right about less, and how'd you get the less? Because the 4 is bigger than the 2.
Yeah, 108.
Yeah, 108. Okay. You see how that works? 108. Cool. All right. Looking good. So, kind of starting out talking about the atom, we're kind of careful about making sure that the number of protons in the nucleus, the number of protons in the nucleus are balanced by electrons in the cloud outside the nucleus. That makes what we call a neutral atom. But that's not always the case. So the word ion simply means that you don't have the same number of electrons outside the nucleus. There's either more electrons, which makes it negatively charged, or there's fewer electrons outside in the cloud, and that makes it actually positively charged. Okay, so those are both what we call ions. Now, as we talk about ions just means it's lopsided. An atom is lopsided. It doesn't have the same protons as electrons. Keep in mind that the protons, and this took me a while when I was teaching this, keep in mind the protons in the nucleus, they're like never going anywhere. It's the electrons that kind of come and go. Protons are stuck. Okay. So a neutral atom will have the same number. Okay, and the cool thing is that charge-wise, the magnitude of the charge Each one of each plus the magnitude of the charge is equal. They're just opposite. So we talked about this jag, okay, and this jag separates metals from nonmetals. And the way this works is metals, which by far most of the elements are metals, will tend to lose or kick off electrons. So if you kind of picture what's happening as a metal, and this isn't, carbon's not a metal, but if as I take off an electron or two, and if I do the math, then that's going to mean it's going to be heavy with regard to a positive charge. And that's why it makes it what we call a cation. It's positively charged. Okay. So the word is cation, sometimes called, cations. Cations? It looks like cations. Cations. Now, the nonmetals do the opposite, and we'll kind of talk about why metals kick off electrons and nonmetals take in electrons. But, so these guys, these kind of triangle guys, or these guys located in the triangle periodic table, these are your nonmetals, and they actually will pick up an electron or two or three, and then you can kind of see, and carbon is a nonmetal, we can see that as we add electrons on, now when we do the math and try to see if it's charged or not, now we have more negative particles than we have positive particles. So it's going to be negatively charged, what we call an anion. Sometimes affectionately called an anion. An anion. Okay. So this is we talked about the group number is the number of valence electrons in an element in that group. So boron has 3A, 3 valence electrons. So they're kind of shown here. Aluminum, they both have 3 valence electrons. Okay. So here's what happens. And again, we talked about different parts of the periodic table, and the A are called main group elements, sometimes called representative elements. So this is A, okay, A. And then this is A, and that's all I'm talking about right now. I'm not talking about the B, the transition elements, or the intertransition elements. So here's the deal with regard to those guys. The metals will lose the number of electrons to get like the rare gas in front of them, and the nonmetals will pick up electrons to get like the rare gas in front of them. So let's pick on the metals first. The metals first. So here's what this looks like. And again, as electrons kind of come and go, we form ions. Think of the heart, the nucleus of the atom staying the same. So it doesn't really change its identity. So this says, for instance, all the 1A metals, okay, what they will do is kick off, let's pick on potassium. If it's neutral, it has 19 protons, and if it's neutral, then it will have 19 electrons. What potassium will do, like this slide says, is kick off 1 electron. And can you see now it has 18 electrons, which is like, which is like argon. So it's the period before it, the rare gas of the period before it. Well, potassium kicks off 1 electron, then it's going to be a +1 charge. Now this is where, if you have your periodic tables handy, this will help you down the road. These guys right here at the top, sometimes I tell students go ahead and put a +1. +1 means that that's the charge that they will form. They will form a cation. Okay. 2A will kick off 2 electrons. So we picked on, see, who did we pick on? Potassium? Well, if we go one over, calcium, check this out. Calcium is going to kick off two electrons to get like argon, okay? So it's still going to be calcium, to 20 protons, but now it's only going to have 18 electrons, which means it's going to have a net +2 charge. So I usually tell students put a +2 at the top of that column. And then we're going to skip these guys for now. They actually, since they're metals, they do kick off electrons, but it kind of varies. And then we want to stick with the metals. So now we're going to go over to aluminum. Now, the reason I'm not picking up boron is boron a metal? No. Boron actually is kind of, I think it's a non-metal, not a metalloid, okay? So beginning with aluminum, these guys right here, so this is where you might have to take a little +3 and kind of put it, draw an arrow above aluminum, okay? So aluminum, gallium, indium, thallium, and whatever NH is, okay? Those elements will kick off 3 electrons to get a rare gas configuration. Now this is where it gets a little weird because you're like, wait a minute. If aluminum, pick on gallium. If gallium loses 3 electrons, 31 minus 3, you're looking at 28. Well, that's not like a rare gas, and this is where you'll just have to kind of take my word for it. It does end up being like argon. Because these actually electrons are added, they're kind of what we say inert electrons. Okay, so those are cat ions. I like cat like T in cat.
Is it like the going, like 4, 5, 6?
Yes, if it keeps going, not necessarily.
Oh.
Yeah. The trend that you can hang your hat on is the trend I've said, the 1A or +1, 1A metals. The 1A, which they're all metals, the 2A metals, which are all metals, are +2, and the 3A metals, so beginning with aluminum, are +3. Sorry to say, the 2A are +2, and the 3A are +3. And you can't hang your hat on the others. But you can hang your hat on this other trend. So the metals form positively charged cations, and the non-metals form negatively charged anions. And this is a little easier to visualize. Again, when something forms an ion, its heart stays the same, so it's still that element. It's just kind of losing or picking up electrons. So what this says is that the 7A, these guys right here, these halogens, will gain 1 electron to get like the rare gas in front of them. These are easier to see, I feel like. And if they gain 1 electron, they'll have a -1 charge. So above the 7A, I put a -1, as in that's what charge they'll form. And above the 6A, they pick up 2 electrons. These all pick up 2 electrons. Now again, I'm just limiting these anions to the non-metals. Okay, so I put a -2 over 6A, and over 5A, just those 3 elements, because you can't go on the other side of the jag, just those 3 elements there will pick up 3 electrons. 5A will be a -3 charge. So, -3 anion. Cool. All right, I can't remember, so we'll just start over again with you, David. So David, help me out. So you have to find it on the periodic table. So Na stands for sodium. So what charge would it form?
Well, like adding 1, right?
It will actually kick off 1 electron, and it will be a +1 charge.
Oh, yeah.
Yeah, yep. Oh, you're fine. Thanks. Yep, it will be a +1 charge. So every once in a while, students will be like, oh, I'm going to put -1 in front of that on the column because I know then the minus means it kicks off an electron and becomes a +1. But I usually know what charge it's going to be. It kicks off an electron. So either way. Melissa, and find it on the periodic table. Oxygen?
-2.
Yep. I've got it on my sheet, don't I? Okay. Bromine? -1. Magnesium? +2. +2. And you guys know where these are coming from, right? And nitrogen, David? -3. You got it. Yep. -3. Perfect. Melissa, potassium?
Where's that on here?
So it's kind of over on the
Oh,
left side.
+1.
Yep, +1. Very good. Kaylee, sulfur? -2. -2. I'm digging it. Very good. Genesis, fluorine?
-1.
-1. Cool. Back to you, David. Calcium?
+2.
+2. Yep, very good. And last one, P phosphorus. Melissa. Kind of on the rightish, sort of. -3. Very good, you got it. And it's gonna be, it won't be today, but it'll probably be, I don't think it'll be Friday. But this is so cool. So we have all these negative pieces, negatively charged anions and positively charged cations, which is kind of an assortment here. There's one type of compound called an ionic compound, and all it does is go ahead and pick something that's positively charged, something that's negatively charged, and put it together and make a compound. What is the formula for table salt? What do you think? Can we know?
Sodium chloride.
It is sodium chloride, very good. Sodium chloride, so sodium is Na and chloride is Cl. Okay, so what charge is sodium if you find on the periodic table?
+1.
+1. How about chlorine?
-1.
-1. So here's the deal. This is table salt, and actually, how do I say this? You have one sodium and one chlorine that goes together. Can you see where if I have one of these and one of these, that makes that whole compound neutral? Does that make sense? Okay, talk about that. And because if I switch it up, that's an awesome compound. But what if I pick something that's instead of chlorine, what if I pick sulfur? So you're like, dang, and my board's getting kind of messy right here. Let's just kind of a look at one of the things we'll be talking about. If I go ahead and I want to combine sodium with sulfur, what charge is sulfur if it's an ion?
-2.
It is a -2. So here's where, and again, we'll talk more about this, but if I wanted to make it neutral, I'd actually have to have 2 of these. So actually the formula for it is Na2S. Okay, and the reason I need 2 of those is because it's only a +1, and the sulfur is a -2, and that gives me a neutral formula. So, but again, okay, so back to atoms and all that. On your test for this unit, I might ask you questions about this idea of how many protons, how many neutrons does something have, and how many electrons does something have, using this sort of shorthand notation, where there is no element X, or they're only in like Powder Puff Girls, I think the professor has. Yeah. So in this shorthand notation, you're going to see mass number in the upper left, that's the number of protons plus the neutrons. This guy right here, number of protons plus number of neutrons. Atomic number, that's just simply number of protons. And then the charge, if there is a charge, in the upper right-hand corner. If that's blank up there, it means it's neutral. Okay? So it would look like this. We'll go backwards. I can never. So Genesis, I'm gonna pick on you. Do you guys already have the answers for these? That's kind of fun. Okay. So F stands for fluorine, and to me, if you have the symbol for fluorine, you can look up the number 9. But 9 is what we call the atomic number. The mass number is 19 in the upper left-hand corner. So to get the protons, we just need a 9, okay? To get the electrons, since it's neutral, and I know it's neutral because there's nothing here in the upper right-hand corner, no charge, it's free. So I must have the same number of electrons as I do protons, which is 9. Neutrons, I get by subtraction, basically the big number from that, so you subtract the little number. So you get 19 minus 9 is 10. This one's a little bit different. Ca stands for calcium. And for this one, it's not neutral, so I'm going to have to do something a little more interesting with the electrons. Of course, This is consistent with what we've been talking about. It's a 2A, so you would put a +2 over there, meaning the charge it forms when it loses 2 electrons. So protons, we can pick off 20. Electrons now, it has to have 2 less than that, so 20 minus 2 is 18. Neutrons we get by taking the big number from that, subtracting the little number, because that 39 is protons plus neutrons, and the 20 is protons. So we get 19. Chlorine, if we were to find it on the periodic table, you're looking at chlorine being one of the halogens, so it's 7A, and you put a -1 is the anion that these elements will form, or -1, excuse me. And so protons, it's shown here, it's the smaller number on the lower left, so it's 17. We could have gotten that from the periodic table too. This particular isotope has a mass number of 36. 36 is protons plus neutrons, so we can take 36 minus 17 to get neutrons, but we're not quite there yet. So electrons, you can see that it has one extra electron, because it's a -1. And so we're going to take 17 plus 1 to get 18 electrons. Neutrons, I kind of got ahead of myself, but it's always the mass number from that subtract the atomic number. So 36 minus 17 is 19. Okay. I think that's a good place. More slides. Okay, let's finish it, guys. All right. Well, no, because there's a video. I think we should wait till Friday. Yeah, we'll wait till Friday. Okay. But we'll start the next part on Friday. In the meantime, we have lab tomorrow.